now we're going to talk about orbital mechanics, and we're going to talk about Kepler's 3 laws of motion. So you should be able to state Kepler's 3 laws of motion. So his first law of motion is that a planet is going to go around a star in an ellipse. So you should be able to make this picture. So there's the star, and then that is an ellipse. So notice that the star is not in the middle of it, it's off to the side a little bit. And then the planet is over here, and it's in orbit around that star. So that's his first law of motion. Now his second law of motion is a little bit more complicated. A planet will sweep out equal areas in equal amounts of time. So let's pretend that the planet is here, and let's say that it's June. And we're going to let the planet orbit for 1 month. Now it doesn't make any difference the time, as long as you use the same time on one side as you do on the other side. So let's say 1 month. So let's say that the planet orbits to right here, and then we can join those points together, and that makes it kind of looks like a triangle, but it's really it's called a sector. And we could actually mathematically calculate what the area of that sector is. Now let's wait until the planet orbits to somewhere else. So now let's say that the planet is up here. Now we're going to wait 1 month. So let's say that it orbits down to here. In 1 month it goes from here over to here, and then we connect those points, and then we can mathematically calculate what that area is, and it would turn out that this area is going to be exactly the same as this area over here. Now Kepler had no idea why that was true, but it's conservation of angular momentum. So the angular momentum, when it's over here, is going to be the mass times the speed of the planet times how far it is from the sun. And then it's also going to be the same angular momentum when it's over here. So over here it's still going to be the same m that it was before, but the r is going to be smaller because it's closer to the sun, and because the r got small, the v got big. So it's moving faster when it's over here. And that's why this distance from here over to here, do you see it's much larger than this distance from here to here. So if you're going faster, you can cover more distance. So therefore, the reason for his second law of motion is it's just conservation of angular momentum. It has the same angular momentum over here as it does over here. Okay, then you've got the third law of motion. So his third law of motion, and the only one that you have to be able to calculate with, is going to be this one. So it's going to be the period squared is going to be equal to the semi-major axis, and we're going to use the letter R, and we're going to say that it's the distance from the star to the planet. Now actually it's the semi-major axis, but we're assuming that the orbit is basically a circle, so that we could use the radius of the orbit as being the r. And then it's going to be r cubed. So r raised to the third power. So you should be able to calculate using that formula. So here's an example of how that you would use it. So you should be able to do that on the exam. The distances are in astronomical units. An astronomical unit is the distance from Earth to the sun. That's 1 astronomical unit. And then the time period that comes out of this T thing is going to be in Earth years. So this is in astronomical units. This will turn out to be in Earth years. So be able to make a calculation like that. But I would also like for you to recognize that this formula is incomplete. So this was the one that Kepler came up with, but in actuality, you also need to include mass in this formula. And so that M in the bottom part would be the mass of the planet plus the mass of the star. And then that should actually be part of the formula there. And then you can also see that it should also include big G, because big G is in our formula for gravity here. But let's not worry about that. So what I want you to be able to do on the exam is state Kepler's 3 laws of motion and then be able to calculate using that formula. Okay, so let's take a break, and when we come back, we're going to talk about other kinds of orbits.